Great. So, let's start. Hello, my name is Vincent Kivis, and I'll be the reporter on problem number 9 as the screws are made by Greece. Let's move on to the problem step. When placed inside in a ramp and released, the screw may experience synchronous oscillations as it goes down the ramp. Our task was to investigate how the motion of the screw as well as the growth of these oscillations depend on the relevant parameters. Now, here's the overview of the theoretical model. So as you will see, we decompose the motion of the screw into the two axes, namely the vertical axis in which sliding movement occurs, as well as the horizontal axis in which an oscillatory movement occurs. So as far as the screw itself is concerned, first of all, we model the screw as a cone, later as a cone of pendulum with a fixed pivot point, as well as a couple of pendulums with moving pivot point. The moving pivot point itself was divided into two phases, namely phase A and phase B, which we will also later discuss during the report. Now, here's the sliding movement of the screw and back to force analysis. As you can see, there are three main forces acting upon the screw, namely the weight, the normal force, and the friction. The weight itself is composed into the z-axis and y-axis, so as to ensure that we get the sliding acceleration of the screw, which equals to g sine theta minus n minus v cosine theta, which will be replaced by the second law. Now, onto the oscillating movement itself, which is the more complex movement. Now, as we said, first of all, we model the screw as a cone. So, as you can see here, this is an isometric view of the cone. And our theory is the following. So, whenever a rigid body has a non-zero angular velocity omega, there is something called the instantaneous screw axis, ISA, which is basically the green line that you can observe away. As you can see, the instantaneous line of contact with the plane. And the important thing here is that every single point that's coinciding with this specific line. So this means point B and point C. Even though these points might have a velocity component that is parallel to omega, they are also referred as poles of the instantaneous screw axis, just for the sake of simplicity. However, we derive the equation that we derive using the bibliography on the very is the resulting equation for the velocity for the rotation of the cone on the circle defined as xy is the following formula that you can see on your slide. However, there is an issue with this formula, and the issue is that this formula is unable to explain the growing factor of the oscillations that are present in our experiments. As you can see in the formula, they are like we can only see how the velocity changes when the screw travels down the ramp, and not how the vertical movement of the screw affects the oscillations at all. So that's why we discovered the modeling of the compound pendulum. So we thought of using such a modeling, not the cone. So give a brief definition of the compound pendulum. The compound pendulum is one in which the rod is not massless, and it can also have it stands here in extensive size. So it's actually a random shaped body, so we don't really care. In our case, this is obviously a chemistry that is swinging by a fixed pivot point, but it can be a random body. There is no issue. We can still model it. That's a common kind. So in our case, let's say that P is a pivot point. C is the body's center of mass, and then body center of mass is obviously located at this distance from the pivot, so as this distance equals to BC. So let's say that delta is the angle between the downward vertical and the line BC. So if we take all this into consideration and then take the screw from the limit position by the angle that we have already said, then mg sine theta will actually exert a restoring torque on the opposite direction. So we tilt the screw on the left hand side and exert a restoring torque on the left hand side, so as to restore the equilibrium position that the screw had, right? Now, the formula for the torque is the following that you can see on the right-hand side. And if we want to find the acceleration, so how fast the screw actually will, the acceleration of the screw in this specific axis, then we just need to divide it by the moment of inertia, and this is the formula for the angular acceleration of the screw. Now, this modeling, as we said, we want the common angle, the fixed pivot point, and the small pivot point. This modeling was for the fixed pivot point. So as you can see here, obviously, the greater the sliding acceleration is, the greater the growing factor is as well. Now, if we want to model it as a moving pivot point, then the effective value of z sine theta will be z sine theta minus a. So, just for the sake of the demonstration, so here we have an elevator, so as to explain why is g sine theta minus a. So, if an elevator is stationary or it is moving with constant velocity, then the normal force acted upon the body, in our case, sphere, equals to the weight of the sphere. However, if the elevator accelerates upwards, then the normal force will be m times g plus this acceleration plus c. However, if the elevator accelerates downwards, then the normal force will be m times g minus this acceleration a. So, in our case, we have the third option, namely the part that accelerates downwards, and therefore the normal force equals to m times g minus n. Now, that's exactly the reason why the effective value of g sine theta will be g sine theta minus a if we want to model it with a moving pivot point. However, the issue here is that we have in the formula of the angular acceleration, we do also have the slide and acceleration, so that's an issue. And in order to, for simplicity matters, and so as to cause no confusion at home, we need to solve the formula for the sliding acceleration for minus g sine theta minus a, so as to have at the end in the formula, instead of g sine theta minus a, we have minus g and cosine theta. Now, if we do so, then we come up with the second order nonlinear ordinary differential equation, which is the following equation that you can see on the bottom of your screen. Now, for this differential equation, we did an approximation. For small angles lower than 30 degrees, we did an approximation that sine theta equals to delta, we need the radian of this angle, and obviously not the radian, the angle itself. Now, if we solve this differential equation for delta, we need to find, we did so that we can find, as you see here, the screw's angle of inclination. So the most important parameters here that perhaps we're not so that familiar with is that we define theta as the angle of inclination of the plane, and delta is the initial screw angular displacement. Now, here's our experimental model, as you can see, and it consists of the screw, as you can see on the left-hand side, the wooden round, and we did also use the software tracker. So some specifications about our experimental setup are the fact that the rolling coefficient of friction is 0.01, the coefficient of friction, this static one is 0.65, whereas the dynamic one is 0.4. The length of the screw 0.03, whereas the mass 0.0045, and moment of inertia 0.07. Now, let's go on to our hypothesis. So our first hypothesis, as we previously said, we divided the motion between two phases. Phase A consists of an angle that is lower and an angle of displacement that is lower than 30 degrees. Our first hypothesis is the following. Until the screw reaches its maximum displacement of 30 degrees, the oscillation is highly harmonic. As you can see here, our hypothesis was indeed confirmed, we started from 25 degrees, and as we reach the endpoint of 30 degrees, you can see here that the oscillation is actually highly harmonic. However, for initial angles that are higher than 30 degrees, the growing factor in the oscillations is actually present. So in our case, we started from an angle of 60 degrees displacement, and we reached an angle of 90 degrees. So this angle of 90 degrees, you can actually observe it as soon as the screw touches the floor. I mean, you can see it's right before it touches the floor. So our next hypothesis was that by increasing the angle of inclination of the plane, the period of the oscillation will also be increased. So we started from a 30 degrees angle of inclination of the plane, and then we varied it by 10 degrees until we reached the final point of 60 degrees. And our hypothesis was once again confirmed by increasing the angle of inclination of the plane. The period of the oscillation is also increased. So the important thing here is the fact that the dependency between the period and the angle is actually pretty linear. And as you can see here, it's not exponentially or quadratic or etc. So the important thing for us was that the dependency was actually linear. And here once again, you can see the equation that we used for the screw's angle of inclination. Here's once again the sum of the report. As we said, first of all, we modeled the screw as a count and found that this was not actually the case. Then as a common pendulum, which really helped us with fixed pivot point and with a moving pivot point. And in the end, we presented our three hypotheses, and all three of them were indeed confirmed. So thank you very much for this.
Okay, thank you very much. Team from Greece. Team from Chinese Taipei, time for your initial questions.
Okay, can you hear me? Thank you for your report. First of all, is it dynamic friction or static friction acting on the screw? And yes, and do you agree that friction is acting on the two contact points? Do you agree that friction is acting on the two contact points? Okay, thank you. So the two friction on two contact points is different. Do you agree with that? Okay. And will the magnitude of friction be constant throughout the oscillation? Will the magnitude of friction be constant? And like the value of friction. Okay. And did you investigate the boundary condition for green oscillation? Okay. Do you investigate the motion of the screw instead of the angle, like the motion? And I mean the experimental results. Do you investigate the motion?
贴到耳机那个
沙对啊，
真的？不是啊，不是啊。
那很奇怪，我
不然你等下我再。
跟你的笔差。
那我等下再。
那这个我就找了这样，这个
这样是 incline
projector。那放 room observation，它的角度没有很大。
你看这头挡啊，我头挡。
那个是有人去。
哦，为什么？
现在几分钟？看一下。
他说他已经换过了，那我再换一个。
This parameter
上面只有 B， 跨 5 2， 那你要得跨下来那个 Stage。你在等一下。哎，你要分享了。
你可以分享，他说他已经换过了。
他分享了。他分享了。好，看看分享。
之前多少吧？5分钟准备。
真的吗？
对吧？他为什么这个？
跟我不知道时间到不到了没？
为什么他的时间
你先分享吗？
你可以跟他说 excuse me， 可以咖啡。我要是这个。
没有了，那个。你先分享。
没有，先分享。
啊。
然后几个。This parameter reflection coefficient， 然后什么？angle， 叫什么？
还有一个。
还有那个尺度。There is a linear field. Teacher.
不用看就会讲。
好上去了。有。那时间就放给大家看。
那你就不用拍了，就拍死走。
算了。因为我这里跑不去。听我声音。然后这里有。
Again, it's a time guide. We've had about 4 minutes preparation.
Okay, I'm ready. Uncle Dries and all competitor. I'm the opponent from Taiwan, opposing problem number 9, oscillating screw. And this is a problem statement. We mainly focus on the motion and also the growth of these oscillation. And I believe the reporter analyze the oscillating angle. However, they didn't analyze well with the motion of a screw. And this is a phenomenon. So the phenomenon is that a screw will have a growing oscillation, and the peak of the oscillating angle will grow, and the screw will size down because of the tangential velocity difference. So they analyzed the kinetic friction coefficient. However, they didn't have a good analysis of the quantitative definition of growing oscillation. And for a theoretical model, they consider the friction coefficient, and also they calculate the friction and also gravitational component. However, in the short question part, he agreed that the friction is actually acting on the two contact points, and it's different because of the normal force is different. However, they only consider one kind of friction in their model. And also the gravitational component is acting on the gravitation in the center of the mass instead of the head of the screw. And also they ignore self-rotation in the theory. Then for the experimental part, in the first case, which is a small angle, it will have a linear period when angle increase, and it is a harmonic oscillation. They explain the reason that caused the motion. However, they lack of analysis of the energy change through the oscillation. Since we know that the screw size down, the potential energy will transist to kinetic energy, and also the energy consumed by friction. And they didn't find growing oscillation in their theory. They only show the period in their theory, and the oscillating angle is the same. And they didn't show the boundaries of the phenomenon, like if we increase the inclined angle, like how many, what's the value of angle that the growing oscillation will happen. Then for the experiments about the releasing angle, they analyze the oscillating period, and they show that it's actually a harmonic oscillation, and because of the assumption of the, I believe because of the assumption of the structure, that causes the unexpected deviation. Then in the modeling part, and this is the point I'm going to discuss later. So first of all, I'm going to discuss the main cause of the oscillation, including the energy transformed through the oscillation. How do the potential energies transist to kinetic energy? And by noting this, we also want to discuss the energy dissipation, which is mostly from kinetic friction.